Let's study 9th standard ICSE chapter 6 of chemistry, hydrogen. It's a very light chapter. Hydrogen is the first element in the periodic table, probably the first element created in the universe billions of years ago after the Big Bang. Most of the universe is filled with this gas. All our stars, including the sun, has a lot of hydrogen. So it's a very important element. We remember hydrogen to be placed here in group 1 and period 1, although that's not its fixed position. Many scientists argue that it could even be placed here in group 17 because it has properties similar to halogens as well. Or perhaps it should just be kept separately in the periodic table. Its atomic number is 1, mass number is also 1 because it has only 1 proton, no neutron, and 1 electron, of course. It doesn't exist in the monoatomic state. It is a diatomic molecule. Its valency is 1. It can give or gain an electron to be stable. If it gains an electron, it will have the electronic configuration of the nearest noble gas, that is helium. So because it has only one shell, we place it in period number 1. And because it has only one valence electron, we place it in group 1. Now hydrogen has a split personality. Sometimes it behaves like an alkali metal and sometimes like a halogen. So let's study its similarities with alkali metals. First, its electronic configuration. If you look at any alkali metal, they have all one valence electron. So that is 1 point. So this 1 and 2, these 2 points are one and the same actually. Valency is 1, just like alkali metals. Ion formation, yes, just like any other alkali metal, it loses an electron to form a cation. So they are all electropositive in nature. Reducing power. So in this reaction, you can see just like sodium is taking away the oxygen and acting like a reducing agent, even hydrogen acts like a reducing agent because it can take away the oxygen to reduce copper oxide to copper. And it itself got oxidized from hydrogen to form water. Burning. Well, it burns to form the respective oxide, which is called dihydrogen oxide. By the way, it burns with a pop sound. Alkali metals also react with oxygen to form their respective oxides. Because alkali metals are extremely reactive, they react with the moisture or even the oxygen in the air, we don't expose them. We keep it in inert organic solvents like kerosene so that they are not in contact with moisture or oxygen in the air. Combination with nonmetals, well, just like sodium or other alkali metals form oxides, sulfides and chlorides, hydrogen also forms its oxide, sulfide and chloride. So that's also a similarity. Sometimes it shows similarity with halogens. Electronic configuration, well, just like all of them have one electron short of completing their outermost shell, that is true for hydrogen as well. And its valency is also 1, although in this case it will gain 1 electron. And when it gains 1 electron, it forms a negative ion, an anion, just like halogens do. So it has an electronegative character. Just like halogens, it's a gas. At least fluorine and chlorine are a gas. Alkali metals, not a single one of them is a gas. Yes, bromine is a liquid and iodine is a sublimatory solid. Atomicity, well, alkali metals are monoatomic, but hydrogen is not. Hydrogen is diatomic, and even halogens are all diatomic. In fact, hydrogen has some special properties which neither alkali metals nor halogens have. For example, hydrogen has only one shell. That's it. And hydrogen oxide, that is water, is neutral, whereas halogen oxides are acidic and alkali metal oxides are basic. Occurrence, well, it occurs in the free state in very small quantities and traces in the atmosphere. It is found in volcanic gases as well, but the stars and the sun have huge quantities of it. In fact, the day hydrogen and helium run out, a star will stop emitting light, which would happen in 5 billion years. Don't worry, you won't be there to witness it. In the combined state, it is found abundantly. It is a part of all organic compounds. Carbohydrates, proteins, fats, everything has hydrogen. Preparation of hydrogen. One method is by using some reactive metals. Potassium, well, you just drop it in cold water and you see a vigorous reaction. In fact, the potassium will melt, forming a silver grey globule, and that will dart about on the surface of water vigorously. It's an exothermic reaction, and so much heat is produced that the hydrogen may catch fire and you'll see a lilac colored flame or purple flame out here. And what is formed is potassium hydroxide, which is an alkali, so the solution becomes soapy. So this is not a nice way of producing hydrogen. It's very risky. Let's study sodium. Is that good enough? By the way, the lilac color flame was because of the traces of potassium vapor. Sodium also floats on water. It's a very light metal. It also forms a silvery globule which darts about on the surface of water. So to hold it still, we may need to use some other equipment. For example, we may have a wire gaze or this tube holding it in position. And it's an exothermic reaction. It's so hot that it can catch fire. The hydrogen can catch fire, but this time it will give you golden yellow flame because sodium vapors are golden yellow in color. And what is left behind is sodium hydroxide. Instead of using pure sodium, we can use a sodium alloy, that is mixed sodium with mercury. It's called amalgam, sodium amalgam, which is safer. Calcium is less vigorous, so we can use that. And calcium sinks in water, and bubbles of hydrogen can be collected over the water. So the method of collection is downward displacement of water. Earlier it was completely filled with water. Then as the hydrogen is getting collected here, the water is being pushed down and out. So it's safe here. It won't come in contact with any spark because hydrogen is very combustible. The solution is calcium hydroxide, which will turn blue litmus red, of course, and it will be a little turgid because calcium hydroxide is not completely soluble in water. It's only slightly soluble in water, so it's in fact called lime water, so it will turn milky with time. So I meant that the red litmus will turn blue because it's an alkali. But we don't use this method also because calcium is very expensive. So let's try magnesium now. Now only sodium, potassium and calcium could react with cold water because they're very reactive. Magnesium onwards, the metals of the activity series are not so reactive. So we'll have to use boiling water or steam perhaps. So when you use steam with magnesium, you get magnesium oxide and hydrogen gas is released. Now that's another difference here. Earlier, we had potassium hydroxide, sodium hydroxide and calcium hydroxide being produced. But now with steam, oxides will be produced. By the way, only for magnesium, we have another reaction in which if we reacted with boiling water, not steam, we can get magnesium hydroxide. But this is more important. The oxide is formed. And this layer of magnesium oxide crumbles with heat so that the magnesium will continue to react. Otherwise, if the magnesium oxide layer is formed around magnesium, it would no longer come in contact with the steam. Then the reaction would stop. This is the diagram for that. Like calcium, magnesium is also expensive, so we can't use that. What about aluminium? Well, it will react with steam to give aluminium oxide at 800 degrees Celsius and will give you hydrogen gas. But the problem is that the aluminium oxide creates a coating around the aluminium so that the further reaction will stop. Then you have to heat it at a very high temperature to crack the coating, expose the aluminium once again to steam, and for the process to continue. So that's not a very convenient way to produce hydrogen. Let's try something else. Let's try zinc. Yep, zinc will also react with steam, and it's very important that in your equations you write steam, because if you don't, it's assumed that it is reacting with H2O water, but it doesn't react with water. It reacts only with steam at high temperature to give zinc oxide plus hydrogen. So the residue left behind is yellow when hot and white when cold. So this seems to be a good method. Iron, well, iron is again very less reactive. It's below zinc in the activity series, so it will react with steam, but now the reaction is reversible. So remember, this is one reversible reaction. It forms triferric tetroxide, or simply saying iron oxide. It's reversible means that this can react with the hydrogen formed to give you back these reactants. So not a very convenient way of producing hydrogen. It is reversible. We can produce hydrogen from a non-metal called carbon also. When you react carbon with steam, we get carbon monoxide plus hydrogen together. It's called water gas because if you burn these two together, you'll get water. But you can see here hydrogen is being produced. But then it is impure because it is combined with the carbon monoxide gas. So we'll have to get rid of this carbon monoxide. We'll study more about it soon. So based on this reactivity, we have an activity series. किटकैट नहीं, कैडबरी मांगो, अलादीन, जिंदगी फिर भी प्रॉब्लमेटिक है, कोलगेट हटाओ और अपनाओ पेप्सोडेंट, platinum. So that's how you can remember the arrangement here. Remember that these metals below hydrogen will never produce hydrogen in any reaction with an acid or with steam or something. Even lead won't react much because the moment you start reacting lead with an acid or with steam, it produces an insoluble coating on it, which will stop further reaction. So we can't really react it much. So this is the displacement which we already studied about. Now let's see the reactions of these metals with acids. Now sodium, potassium, calcium will react explosively with acids. Dilute acid, by the way. So we can't even think about using that for producing hydrogen. Magnesium, aluminium, zinc, well, they react with the dilute acids to give the respective salts and the hydrogen gas. You need to know the formulae well. Iron also reacts. Lead won't really react because as lead starts reacting, it forms an insoluble coating of lead sulfate or lead chloride, which will stop the further reaction, and this coating doesn't even break apart. The reasons why we would not use any of these is because they are either violently reactive, or they are expensive, or they form a coating. Iron releases some impurities, and of course metals like copper and mercury cannot react with acid at all. The only metal which is useful is zinc, so we'll study that in detail soon. By the way, not only acids, there are some metals which react even with hot and conc alkalis to give you hydrogen gas. Well, specifically there are only 3 such metals, so they are called amphoteric metals because they react not only with acids but also with alkali. The 3 metals are zinc, lead and aluminium. So learn their reaction, see how they form a salt and hydrogen. The salts are complex salts, zincates, plumbites and aluminates. No need to write the word meta, you just write aluminate. But please write hot and conc below the alkali while practicing equation. Note here there is plus H2O, but here there is no plus H2O. Now let me prove why these metals are amphoteric. If you take their oxides or even their hydroxides, you can see that they will react with acid to give you salt and water, and they will also react with alkali to give you salt and water. So they have a dual nature, so they are called amphoteric. Just like amphibians can live both on land and water, they can behave like acid or base to neutralize the opposite entity. Now let's talk about the laboratory preparation of hydrogen. So we will use granulated zinc. If they are granulated, then it increases the surface area. But more importantly, granulated zinc has some impurities called copper, which acts like a catalyst. Hence it is preferred. So we have this thistle funnel. Make sure the tip of the thistle funnel is submerged in the solution out here, so that whatever hydrogen is produced doesn't escape through it, but rather goes through the delivery tube here. Pour dilute sulfuric acid or dilute hydrochloric acid through it. Don't use nitric acid. The hydrogen is now collected by downward displacement of water. Remember that. Yeah, it was initially filled with water, but then the hydrogen is being collected here, so water is pushed down and out into the beaker. Since it is above water, it is not in contact with oxygen, and so it won't undergo any combustion because of some accidental spark. So that's the precaution we have to take here. Don't bring anything which produces spark near it. And the good news is that the hydrogen is almost insoluble in water, so it won't dissolve in water. So that's why this method works. If you would have just collected it in air, in a test tube filled with air, then when it comes in combination with oxygen, it's an explosive mixture called detonating mixture. One spark and then boom, your hair will be on fire. Now in this method, some impurities are produced along with hydrogen. They are hydrogen sulfide, SO2, NO2, phosphine, arsine. So all of these impurities are seen here. Carbon dioxide, water vapor. And how to remove them? Well, just remember this diagram. The equations are not important. Remember that silver nitrate will remove the arsine and the phosphine. So what is left are these. Then the lead nitrate solution will remove the hydrogen sulfide. The potassium hydroxide will remove sulfur dioxide, carbon dioxide and nitrogen dioxides. And finally, the anhydrous calcium chloride will remove all the moisture. So you get pure, dry hydrogen out here. So this is very important. So calcium chloride is called, fused calcium chloride is called a drying agent because it dries hydrogen. We can now collect this dry hydrogen over mercury. If you again collect it over water, there will be moisture yet again, which you don't want. You can use conc sulfuric acid also as a drying agent, but not in this case because it reacts with hydrogen to form water and SO2. So what are the precautions we are taking in this reaction? There should be no leakage because it's a very explosive gas. There should be no flame near the apparatus. And we should start collecting the gas only after allowing all the air to escape. So immediately don't put the delivery tube in this water-filled beaker. Just let some air escape into the air, in the atmosphere, outside air. And once we are sure that hydrogen is coming out, then only put it in this beaker and collect pure hydrogen. If you don't do that, then the air which was already present in this might just come out, which will have some oxygen. And if there is oxygen mixed with hydrogen, that's quite combustible. So, but how can we be sure that hydrogen only is coming out? Well, introduce a burning splinter. It will be put off with a pop sound. Also, the end of the thistle should be dipped inside the acid. I explained that. Now, we are using dilute sulfuric acid or HCl here. Why not nitric acid? Because it's a strong oxidizing agent. It will react with zinc, not to give you hydrogen, but to give you water, thus defeating the whole purpose of this reaction. We want hydrogen, not water. Yeah, if you want to produce hydrogen with the help of nitric acid, you can use magnesium or manganese. Only these two metals will work, not zinc. And make sure the nitric acid is very dilute, like 1% only, 99% water. And it should be very cold temperature. Then hydrogen will be produced. These reactions are there in 10 standards, so not important from 9th standard point of view. So we can't use dilute nitric acid or conc nitric acid because they are strong oxidizing agents. We can use dilute sulfuric acid, but we can't use conc sulfuric acid because even conc sulfuric acid is a strong oxidizing agent, so it will oxidize the hydrogen to form water, and we don't want water. We want hydrogen, so use dilute sulfuric acid. So what's the test that the gas produces hydrogen? Well, it puts off a burning splinter with a pop sound. These are just notes. Okay, this is not the test. This is the real test. So we understood the lab preparation of hydrogen. But what if we have to manufacture it on a large scale? In that case, we have something called the Bosch process. There are 4 steps. So remember 4 steps. Step number 1, hot coke, that is carbon, is reacted with steam at 1000 degrees Celsius to give you water gas, which has hydrogen, and it is an endothermic reaction. That is, it will absorb a lot of heat. Great, we found hydrogen. We formed hydrogen here, but there is a problem. Carbon monoxide is also formed. We want to separate them. So the next step is pass more steam through this water gas in the presence of ferric oxide and a catalyst. And there is a promoter called chromic oxide, which would increase the efficiency of the catalyst. Let the temperature be 450 degrees Celsius. All these conditions are important. And now what is formed is carbon dioxide and hydrogen. And this time it is an exothermic reaction. So finally, we have 3 gases prepared: hydrogen, carbon dioxide, and even carbon monoxide. Some carbon monoxide is still left over. Not everything is converted here. So now we have 2 challenges. 1, get rid of CO, and 2nd, get rid of CO2. So let's see how to do it. First, pass this mixture of 3 gases through cold water under great pressure of 30 atm. The water will dissolve all the CO2, leaving behind hydrogen and CO. There is another method. If you pass the entire mixture through caustic potash means potassium hydroxide solution, it will absorb all the CO2, and what will be left is hydrogen plus carbon monoxide. So we have taken care of CO2 here. Now how to get rid of the carbon monoxide? Well, pass the mixture of hydrogen and CO through ammoniacal cuprous chloride. It's cuprous chloride but dissolved in ammonia solution, so it's called ammoniacal. Write ammoniacal here. So they combine to form an addition product. So carbon monoxide is has been got rid of. So the only gas left now on top is hydrogen gas. You can even produce it by electrolysis of water, which is very easy. Hence, it is omitted from your syllabus. The C part is entirely cancelled, which is a pity, because it would have given you some general knowledge. If it's taught in your school, then let me know. I'll teach it in the lecture. Finally, we talk about oxidation and reduction. Now here we just have to study what I'm explaining. That's it. Oxidation definition is the process in which an atom or an ion loses electrons. That's a definition. But it could also mean addition of oxygen. So if you see any reaction in which oxygen is being added, that is oxidation. Here you can see that zinc lost electrons and became a cation. So it is called oxidation. Second hint of recognizing is addition of an electronegative ion, but no need to remember any examples of this, not at all. Removal of hydrogen. Yeah, in this reaction you can see that chlorine is removing the hydrogen from it and poor sulfur is left all alone. So this is called oxidation. That is, hydrogen sulfide has been oxidized to form sulfur. And who has oxidized her? Chlorine. Another hint is removal of electropositive ion, but just remember the title, not the names. Oxidizing agent. Well, it is any agent that oxidizes other substances and it itself gets reduced. So here, who oxidized hydrogen sulfide? chlorine. So chlorine is an oxidizing agent. So remember, if they ask for examples of oxidizing agent, we already know a few. Chlorine, oxygen. So 2 examples are sufficient. If you want to learn more, all of this, then you can. If your school teacher has told you to learn them. Reduction is the exact opposite. It means when an atom or an ion gains electrons. So here, it was a cation which became neutral by gaining electrons. So this is called reduction. It could also mean removal of oxygen. So here you can see that hydrogen is removing the oxygen. So copper is left alone. So we say copper oxide has been reduced to copper. And who is the reducing agent here? Hydrogen. Similarly, carbon has reduced zinc oxide to zinc. And who is the reducing agent here? Carbon, who herself underwent oxidation. It could also mean addition of electropositive ion or removal of electronegative ion. Addition of hydrogen is called reduction. So chlorine was there. Here, hydrogen was added to it to form HCl. So we say chlorine has been reduced to hydrogen chloride. And who is the reducing agent? H2S. Here again, chlorine was all alone and hydrogen was added to it. So chlorine has been reduced to form HCl again. And who is the reducing agent here? Ammonia gas. And a reducing agent is a substance which reduces other substances and itself undergoes oxidation. And in many reactions, oxidation and reduction happen simultaneously, and hence they are called redox reactions. Redox. And all displacement reactions are always by default redox reactions. For example, here, copper sulfate. If you look at their valencies, copper had a valency of 2 plus because SO4 has 2 minus. Zinc has 0 oxidation state here, no charge here. Here, it forms zinc sulfate plus copper. So you can see that zinc has displaced copper, kicked it out of the relationship with sulfate, and poor copper is left alone simply because zinc is more reactive than copper. So sulfate would love to spend time with the more reactive metal. So here now zinc has a charge of 2 plus and sulfate has 2 minus, of course. And now copper is alone, so it has no charge, 0. So if you look at the oxidation states, that is the charges out here, you notice how CO2 plus has become CuO. That means initially it had deficiency of 2 electrons, but now it is neutral, so it has no deficiency of electrons. That means it has gained electrons. That means it is reduction. On the other hand, zinc had no charge, but now it became 2 plus. Means it became a cation. Means it lost electrons. That means it underwent oxidation. So overall, what we would say is that copper sulfate has undergone reduction. Don't say copper has undergone reduction. Copper sulfate has undergone reduction to form copper, and zinc has underwent oxidation to form zinc sulfate. So here copper sulfate is an oxidizing agent and zinc is a reducing agent. Remember the hint. Metals, just pure metals, are good reducing agents and halogens are oxidizing agents. Let's take one more example. So here, think about it. Which is the oxidizing agent? Which is the reducing agent? Copper oxide became copper. That means it lost an oxygen atom. That means it underwent reduction. And hydrogen gained oxygen, so it underwent oxidation. So it is a reducing agent and this is a oxidizing agent. Similarly here, you can figure out which is the oxidizing agent and reducing agent. So this table will help you to remember all the points. Although point number 3 and 4 are not very important.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.